When we think about diatomic molecules made from two different atoms, we're going to use exactly the same ideas and combine their atomic orbitals into molecular orbitals. And so these molecular orbitals are going to look very similar to the ones that we derived from the hydrogen ion. The difference is that so in this case, we're looking at CO, the atom with the larger nuclear charge, so oxygen in this case, is going to have atomic orbitals that are all lower in energy than the one with the lower nuclear charge, so carbon in this case. That's because the higher the nuclear charge, the stronger the attraction of the electrons to that nucleus, and the lower that energy is for all of the atomic orbitals. So we have to draw our 2s atomic orbital for oxygen lower in energy than our 2s atomic orbital for carbon. Same thing for the p orbitals in terms of the atomic orbitals. Now what happens when we combine our 2s orbitals, the anti-bonding sigma orbital and the bonding sigma orbital are not equally spaced around energies that are equal to each other. In addition, because the oxygen 2p orbitals are close in energy to the carbon 2s orbitals, that allows the 2pz orbital from the oxygen to combine with these s orbitals when we make these sigma bonding orbitals. So remember that 2pz has the right symmetry to combine with the 2s orbitals, and this higher energy 2pz orbital pushes these molecular orbitals up a little bit from where they would be if you were just combining 2s orbitals on oxygen and carbon. So that affects the energies of these molecular orbitals because we get mixing in from the 2pz orbital of the oxygen with these 2s orbitals. When we look at the pi orbitals, so combining the 2px and the 2py orbitals on the oxygen and the carbon, we get our familiar set of pi orbitals and antibonding pi orbitals. None of the other orbitals have the right symmetry to combine with those 2px and 2py orbitals, and so those are pure 2px and 2py combinations. However, the 2pz orbitals have a contribution from the 2s orbitals, and that pulls their energy down from where it would normally be if it was just a pure 2pz mixing. So the energy levels are a little bit more difficult to figure out when you have heteronuclear diatomics, but you can reason out, for the most part, which orbitals are going to mix based on how far apart in energy they are. So if we know that the order of the energies of the molecular orbitals for carbon dioxide are as shown here, we can write out a molecular electronic configuration just like we did for homonuclear diatomics, and we can determine a bond order. So this 3 sigma is a bonding, 4 sigma is an anti-bonding. So these two electrons and these two electrons cancel each other out in terms of bonds. This pi orbital is bonding, and this 5 sigma orbital is anti-bonding. And so we have a total of 1, 2, 3, 4, 5, 6 electrons in bonding orbitals that aren't canceled out by anti-bonding orbitals. And so we have a total of 6 divided by 2 is 3 bonds, and so we have a bond order of 3.